Hello and welcome to Circle Video 3. Today's topics will be relationships between segments and angles in circles. And in order to be successful with today's topics, you will need to remember your information about similar triangles. We need to add to our vocabulary for today. So we're going to define a secant as being a line or a portion of a line that intersects a circle in exactly 2 points. In our diagram here, we have a secant line, which is in red, as well as a secant segment, which is in black. With regard to the secant segment, there are 2 pieces of it that you need to be able to identify. The first of which is the entire secant segment, which I'm highlighting here in yellow. It goes obviously all the way through, but you also need to recognize that it has both an interior and an exterior portion. So from the end point to where it starts to come into the circle, that's known as the exterior portion, and obviously the portion of the secant segment that's within the circle would be referred to as the interior portion. For our first investigation, we're going to start off with 2 chords that intersect inside of a circle, but they do not intersect at the center of the circle. We're going to try to prove that the length of segment AE times the length of segment EB is equal to the length of CE times ED. If you look at where those segments are in the diagram, you'll notice that both AE and EB are segments that comprise one of the chords, and ED and EC are the pieces that comprise the second chord. And we're trying to show that the product of those pieces are equal to each other. To do that, we're going to have to use some similar triangles. This product statement looks a lot like what we would get after we use cross products on a similar proportional statement. So we're going to try to get some triangles here. So let's go ahead and draw in segment AC as well as segment DB. That's going to give us a pair of triangles. We want to show that these are similar to each other. So in order to do that, I want you to first notice that this angle here and this angle here have to be congruent to each other because they are vertical angles. So angle 1 has to be congruent to angle 2. Right. For brevity, I'm not going to be writing all of my reasons. Right. I'm going to look at another angle within the same triangle here, and we call this angle 3. And I'm going to notice that angle 3 is actually an inscribed angle, and it intercepts arc BC. If I can find another inscribed angle that intercepts that same arc, I'll know that those 2 angles are congruent. So I look for another inscribed angle that intercepts that arc, and it turns out that angle 4 also intercepts that same arc. So I can show that angle 3 has to be congruent to angle 4 because they intercept the same arc. This gives me enough information to state that my triangles are similar to each other. So triangle AEC has to be similar to triangle DEB by angle-angle similarity. If the triangles are similar, then corresponding sides have to be proportional. So it must then be true that AE over DE has to equal EC over EB. And once you have a proportionality, then you can use cross products and say that AE times EB has to equal DE times EC, which is exactly what we were trying to show. We can summarize that result into the following theorem. If 2 chords intersect in a circle, then the products of the lengths of the segments of the chords are equal. Notice that it's the segments that make up an entire chord. In our second investigation, we're going to be looking at the relationship of the lengths of the segments when we have 2 secant segments that intersect or come from the same exterior point here. So we're going to try to show that QP times RP equals TP times UP. Notice that QP is the entire secant segment and RP is its external piece. And TP is this entire secant segment and UP is its exterior piece. So again, this looks a lot like the result of a cross product. So we're going to try to get some similar triangles in order to generate that cross product. In order to do that, we do need to create some triangles. So we're going to draw in segment QU. That creates triangle QUP. We're also going to draw in segment TR. That completes triangle TRP. We're going to try to get these two triangles similar to each other. They overlap and they share a common angle, so it has to be true that angle P has to be congruent to itself. We're going to try to use the old inscribed angle trick again. So I'm going to choose one of my angles. In this case, I'm going to choose this angle here of triangle QUP. That angle, which I'm going to call angle 1, intercepts arc RU. And if I look for an angle in the second triangle that also intercepts that arc, I'll find that it's right here at vertex T. I'm going to call that angle 2. So it must be true that angle 1 has to be congruent to angle 2 because they are inscribed angles that intercept the same arc. So now, again, I have enough information to guarantee that my two triangles are similar. So I can say that triangle QPU has to be similar to triangle TPR. And again, that's by angle-angle similarity. Corresponding sides have to be proportional. So the ratio of QP to TP has to equal the ratio of PU to PR. And if we do our cross products, we can then show that QP times PR has to equal TP times PU. This relationship can be summarized by the theorem that if two secants intersect in the exterior of a circle, then it must be true that the length of the entire secant segment multiplied by its exterior piece or segment, however you want to phrase it, has to equal the product of the other entire secant segment multiplied by its exterior piece or segment. That relationship or that product is always a true statement. Our third investigation is going to investigate the relationship between the lengths of the segments when you have a secant segment and a tangent segment that intersect at an exterior point. And again, we're going to use some similar triangles. So let's go ahead and draw in segment QT, which, here we go, creates a triangle QTP, as well as segment TR, which creates this other smaller triangle here. We want to try to show that those two triangles are similar to each other. So we'll go for the obvious first. They both share angle P. So therefore angle P must be congruent to itself. And then we're going to look for some inscribed angles. I'm going to zero in up here at vertex Q. I'm going to call that angle 1. Angle 1 is an inscribed angle that intercepts arc RT. If I look for another inscribed angle that also intercepts that arc, it's right here at vertex T. It's formed by this chord and this tangent segment. So this is my second inscribed angle that intercepts that same arc. So therefore angle 1 must be congruent to angle 2. And by now you've kind of got the gist that I can state triangle QPT has to be similar to triangle TPR, again by angle-angle similarity. And so using our idea that corresponding sides are proportional, it's true that QP to TP is equal to PT times PR, sorry, not times, over PR. And now we're going to use our cross products. So QP multiplied by PR has to equal TP times PT. But remember, PT and TP are exactly the same thing. So another way you can write that is that QP times PR is exactly equal to the length of TP squared. If you relate that back, what we really have is the entire secant segment multiplied by its exterior piece has to equal the tangent segment squared. So these results can be summarized into our next theorem that says if a tangent and a secant intersect in the exterior of a circle, then the length of the entire secant segment, so the entire secant segment multiplied by its exterior piece has to equal the length of our tangent segment squared. Our last topic for this video deals with the angle relationships that you discovered on your conjecture sheet. The first relationship deals with when you have two chords that intersect again inside of a circle but not at the center. Notice that you form 4 angles, 2 different pairs of vertical angles. We're interested in what the relationship is between the measure of one of these angles with the arcs that it intercepts. So angle 1 intercepts arc CD. Its vertical angle intercepts arc BA. It turns out that the measure of angle 1 is equal to half of the sum of those intercepted arcs. To put it in terms of the diagram, it means that the measure of angle 1 is equal to half the sum of arc AB plus arc CD. When 2 secants or a secant and a tangent or 2 tangents intersect outside of the circle, there's a different relationship between the measure of the angle formed and the intercepted arcs. So in this case, we're going to be looking at angle C, and it turns out that its measure is half the difference of the intercepted arcs. And in this case, there's clearly a bigger arc and a smaller arc. So it's half of the big arc minus the smaller arc, which in terms of this actual diagram is 1/2 of arc AE minus arc BD. For just a quick reference, if you had a circle and you had a tangent and a secant, you can see how, again, you have a bigger arc and a smaller arc. So this angle would be half of this arc minus this arc. And if you had 2 tangent segments, then it would look something like this, right? And in this case, your bigger arc would go from this tangent point all the way over around the side to that tangent point, and then your smaller arc would go from here to here. Okay, the last page of your packet is more for you if you want to summarize your notes. You can talk about inscribed angles. You can talk about the measures of angles when they're an interior angle or a measure of angles formed when they're outside of the circle. We will be doing a summary chart in class, so this is a completely optional piece, and hope it was helpful, and we'll be practicing next class. Thanks. Have a great night.